time, so that this one can only take care of this called capacitance. So this will improve the circuit. So basically, in another way to see that, when these two are stable and on, when I'm applying a signal here to turn this on, it should it should trigger a change at the output. So the distance where you are applying the signal from here to the output should be as close as possible. So you will be charging, discharging less number of capacitance. So this is called critical path from the signal which is changing more frequently to the output. That distance is called critical path for signal travel. So we want to minimize that length of the critical path. So path is here 1, 2, 3 transistor, here only 1 transistor. So that is a second technique, it's called transistor ordering. So in your design, let's say, now one of you asked a question in this particular circuit. Putting D here or this ABC block here, alternate them, logically it doesn't make any difference because D is in series with ABC. So I can put ABC down and D above with the supply. But if I give you an information that D is more active than ABC, all these three input, then I have to put D closer to the output so that the critical path, if I tell you that B is more active, right? B among, so let's talk. Do you have the sign pen?
Yeah.
Yeah. The mark, okay, I need that.
Sorry.
So let's draw this block to make it clear. Here I have 4 input A, B, C and D. I am giving you an information that B is most active signal. Now, since B is most active signal, according to transistor ordering technique, logically it will not make any difference, but I want to keep most frequently changing active signal closer to the output. So now we are looking at the PMOS block of this transistor. So B is more active. So now I have to put D here. I'm only drawing the PMOS block. And then ABC here. Here I have 2 transistors. So this is A, that's fine. This is D. This is my output. And then this is my pull down block. Let's not talk about it. I'm just writing a block. Now here B and C are in series parallel to A. So what should be the relative position?
B should be near close to the output.
B should be here, C should be here. If this information is given to you, that B is the most active signal, according to transistor ordering approach, most active signal should be closest to the output. Least active signal can be pushed towards the supply to make sure that you are not adding additional delay. Okay. So the third technique we already mentioned in the last class. If you have a large logic gate, like an 8 input, 6 input, 7 input, 10 input, for AND gate, this is how we implement. Directly implementation, we will get an 8 input NAND gate, followed by an inverter, we get an 8 input AND gate. But this one will have a series chain of 8 transistors because it's 8 input in the PMOS. But that will make the circuit very asymmetrical because on the PMOS block you will have 8 transistors in parallel. Maximum path length for each path will, the PMOS will be 1 transistor. But in the NMOS block, you will have 8 transistors in series. So let's draw the circuit for that 8 input AND gate. So I will have here 8 transistors in parallel. We have 8, 1, 2, 3, 4, 5, 6, 7. So these are all PMOS. They're all in parallel. And then in the so you have the CF. Now in the NMOS block, I will have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. A, B, C, D, E, F, G, H. So in the equivalent circuit, you will have an internal load capacitance here, internal load capacitance here, here, 1, right? 1, 2, 3, 4, 5, 6, 7 internal load capacitance. So while you are making a high to low transition, TPHL, it has to go through 7 resistance, 8 resistance, and 8 capacitance including this one. And here in the worst case scenario, only 1 transistor can be on. So let's say this one. In the TP low to high, it will have only 1 resistance and 1 load capacitance. So this circuit will be extremely slow on this side, very fast on this side. It will be very difficult to make it symmetrical. Then you have to make them so wide that probably each one of them to make an equivalent resistance equal to 1 PMOS, then it will take probably 20 times or 10 times more area than this one. The circuit will be, and it will add so much additional parasitic because of the wider size and everything. So that's why it is not recommended to have more than 4 transistors in series in any implementation. So that's why we can subdivide this 8 input AND gate into these 2 4 input NAND gate followed by a NOR. So that is maximum path length. Here we have 4 transistors, 4, here 2. We can further divide each one of them, right? But then the problem here is, as I mentioned, horizontally 1 stage, 2 stage, 3 stage, 4 stage. So where I am adding horizontal delay because first this block must finish its work for them to, they must wait for them to get all the signal and then produce the result here, and then they will finish their processing, produce the result here. So I am adding horizontally, vertically I am reducing the length, but horizontally I am adding more logic stages. So there has to be a balance. So here is the 2-stage problem, it's a 2-stage problem. So typically, if you can reach up to 4, maximum 4 series connection or 4 input gate, then you should stop there. Unless a design tells you that only thing you have available are 2 input logic gates. Then you have to walk down to this. So this is the basically logic restructuring. This technique is called logic restructuring. So these 3 techniques we just mentioned, technique 1 and 2. One is progressive sizing versus uniform sizing. Number 2, transistor ordering. Number 3, the logic restructuring. That will improve your performance, but none of this technique will change the circuit from logical point of view. Now let us see how input pattern actually affects your performance. Even though you are designing the circuit considering the worst case scenario and you address all parasitics and everything, still depending on the input pattern, your circuit will behave significantly different from the worst case design or the ideal design you came up with, and because it will depend on input pattern. let's say a simple 2-input NAND gate. 2 transistors in series, 2 transistors in parallel. I almost got the door. So, now here, for high to low transition, to produce a logic 0, only option is you have to turn on this one, you have to turn on this one, right? Both of them. If you turn on both of them, that means A equal, B equal 1. In that case, both of them will be off, so out of picture. So this is what I have. So here, let's say, for the time being, let's ignore the internal node capacitance. If both of them are high, what I'm talking about, I have two Rn of A plus Rn of B in series, right? So let's assume that both of them are equal size transistor, so each one of them will be Rn and Rn. So Rn equivalent will be 2 Rn, right? Because they are in series. So that is, so now my propagation delay will be 0.69 times Rn equivalent times CL, right? Now let's say another possibility, A equal 1, B equal 0, or A equal 0, B equal 1. In both cases, in both of these cases, in these cases, what I have, if A or B, any one of them is 1, one of them will be off open circuit. For the time being, let's ignore internal capacity. One of them is open circuit, so there will be no high to low transition. Either A is on for A0 or B is on for B0 in the PMOS circuit. So I will have only one transistor on connecting the output, and we will have a TP low to high. So let's assume that both transistor PMOS A and PMOS B, they are equal size. So each one of them will have a resistance of RP. But only for both of these input combination, only one transistor in the PMOS network on. So the R equivalent of P will be RP, right? So now then in that case, 0.69 RPCL would be my total TPHL, right? Now let's look at the fourth scenario. I'm going top, bottom to up, bottom up. So the last one is A, B, both equal to 0. In that case, both of these transistors are off, out of picture. So I have a scenario here. Both of them are parallelly on, connected to VDD, right? Assuming that they are equal size, let's say this is RP, this is RP. So what is R equivalent? R equivalent of P is RP parallel to RP. If two equal size resistance are in parallel, equivalent resistance is RP2, RP divided by 2, right? If they are in parallel. So now, for that combination of input A0, B0, my propagation delay will be 0.69 RP2. Now look at this combination and this combination. Both will be producing low to high transition, right? For A1, B0, for A0 and B1, for all this combination, I will have a low to high transition because output will have a connection to supply. But as you can see, for one input combination to another input, for this two input combination, A0, B1 or B0, A1, delay is on double, right? Because it is RP2 RP divided by 2, this is RP. Almost 100% more, right? And depending on what is the value of Rn, if your circuit has equal resistance for all, because earlier for symmetry, we want to make the transistor resistance if we do uniform sizing, right? If for any circuit Rn and Rp equal, let's say, assume that so now I have, forget about now 0.69 in CL. These are all common, right? So I have delay equivalent to Rp divided by 2, Rp and twice Rn. If Rp, Rn all are equal size, equal resistance transistor, so I am seeing a 200%, 400% jump. If I go this way, it's a 400% jump, because this is 0.5, this is 1, this is 2, right? So that means the delay will vary more than 100% from one input combination to another input combination. That's why it's a double SO. If you design it for the best case scenario, your circuit will be failing for many, many cases. If you design it for the worst case scenario, most of the cases you will not need that much delay, but for no reason your circuit will be stalled, just sitting idle, right? So you will be basically overkill, over designing. So that's why IC design is a very tricky, complex calculation. You always have to basically look into multiple factors and come up with a closed solution. That's why, and that is why you will never see any microprocessor or cell phone or laptop or a tablet or anything that relies on CPUs or digital computation will never give you best possible the marketed performance. It will be under very, very optimum condition for certain specific set of input signal. So here we did actually a simulation, for the textbook did a simulation for different input combination for a certain input and how time changes. As you can see, some signal is moving up very slowly, some signal is low to high, sharp, depending on basically how the signals are changing. And as you can see, there will be other factors, so it will not be just simple linear change. There are other parasitics that will come into play. So as you can see, in this all possible changes, one is stable, other is in all possible combinations of input and up changing. The lowest delay we got is 45 picosecond. The highest delay was 81 picosecond. So as you can see, this is like a almost 100% variance. And this is calculated in the textbook for a given set of device and load capacitance data. Just need to know. And then fan-in consideration, that is another thing we have to consider. How fan-in, the number of input going into a logic gate. What is fan-in? The number of input signal connected to the input side of a logic gate is the fan-in of that logic gate. Number of destination a logic gate is delivering signal to, that is the number of connection connected to its output is called as fan-out, right? So fan-in and fan-out. So now let us look at the fan-in consideration. If I have, we are talking about why we have to avoid this, right? The series of 8 transistors. Just like let us consider a 4-input NAND gate. This is the circuit of a 4-input NAND gate. So there will appear 4 in series, 4 in parallel. So in the CMOS path, NMOS path, if we want to make a high to low transition, I have to turn on all 4 of them. In that case, the equivalent tau will be, if we use Elmore delay model, let's assume that all of them are of equal resistance. So it will be Rn times C1 plus twice C2 plus twice 3C3 plus 4Cl. If I add one more transistor, then it will be C1, 2C2, 3C, 4C4, 5Cl. So it will increase more than linearly. It's called quadratic dependence on the number of fan-ins mean how many inputs are going in. If I add one more input, I add another transistor in series. If I add two more inputs, I add two more transistors in series, then I am going to add one more term, much larger term. So there is a quadratic dependency on the performance, on the fan-in on performance. Because of this increasingly large factor of capacitance we have to add. So this is actually showing a simulation of that circuit, how propagation delay of the 4 input NAND gate is changing with fan-in. As the number of fan-in increases, low to high will not change that much. Low to high will not, it will change, but it will increase very slightly. But TP high to low, because it has to travel the long series path, as you can see, it is increasing quadratically, not linearly. So this is just to show you the dependence characteristics, how fan-in will change. And then fan-out also will increase linearly. It is not quadratic because every time you are adding something to the output, let's say, something to the output not changing here, that means let's say you have a 4 input NAND gate. It is delivering signal to 1 versus 2 versus 3 versus 4. Every time you are adding something, it will linearly add to the capacitive load. More capacitive load it sees in the output, it will take longer time. And that will increase linearly based on the number of connections you add to the output. We are not changing anything in the series chain on the input side. So that will increase linearly. So fan-in will have a quadratic impact on the performance of the delay. Fan-out will have a linear dependence on the delay, and this is basically showing how the delay is increasing for a 2 input NOR gate or 2 input AND gate and an inverter with the increase of fan-out. So overall, for a CMOS logic gate, the dependency on fan-in and fan-out is expressed by this expression. This is not a formula, we will never use it to calculate anything. It just shows dependency characteristics. Fan-in will have a linear component and will have a quadratic component. Fan-out will only have a linear component. So this expression shows you to a designer that with the change of fan-in and fan-out, how propagation delay, that is performance, will change. So that is the motivation. Because of the quadratic dependency of performance on fan-in, we want to avoid this type of long series chain of transistors. So optimally, if it goes above 4, we should stop there. We should try to break down the logic gate by logic restructuring to make it smaller. So now we are going to introduce a different class of logic circuits other than CMOS. You don't have to basically spend that much time to understand the operation and construction of these logics, new types of logic circuit we are going to introduce, because you already know how to construct PDA network for a CMOS. So, a CMOS is comprised of a pull-down network and a pull-up network connected to VDD, connected to ground, and together they are connected to output, right? This is input. This is output. That is it can be one input, more input, it doesn't matter. This is the basic structure of a CMOS. And this design is called ratio-less design. Microsoft Word will take it as a wrong, incorrect word grammatically, but that is the term used in logic field. So ratio-less design means the relative size or size ratio between the transistors of pull-down and pull-up network, even the sizes within the pull-down network, that size ratio, relative sizes of groups of transistor or individual transistor will have no effect on its functionality as a logic gate. If you have implemented it as a 4-input NAND gate, if connections are correct, it will function as a 4-input NAND gate. Sizes of the transistor will increase or decrease the capacitance and resistance. It will affect your performance, it will affect your power consumption, but it will not affect the circuit's ability to function as a logic gate, whatever the. So that's why the correctness of the logical operation or the functionality of the logical operation will not depend on size ratio of the transistor. That's why this type of regular CMOS circuit is known as ratio-less design. So if there is a ratio-less design, there has to be a design that is dependent on ratio of the transistor, and in digital literature it is called ratio design. So this is the ratio design can come in many different forms and flavor. This is the example of 4 possible options. So basically the main idea here is all the ratio logic circuit will have a pull down network exactly similar to the CMOS. Series for NAND, parallel for OR in the pull down network. Instead of having an complementary pull up network, entire pull up network will be replaced by one single load device. It can be a resistor or it can be a transistor. So there will be no pull up network. Entire pull up network will be replaced by one single load device that can be a resistor or a transistor. And that single transistor that will replace the entire pull up network, that can be connected in many different ways. And will give rise to many different types of ratio logic circuit. In case of resistor, there is nothing. Resistor is a passive device. It has only 2 terminals. And to establish the path, you have to connect it between output and the supply. So for a resistor-based ratio design, only one option, a pull-down network with a resistor connected between output to supply. In case of transistor-based load device, you can connect the gate of the transistor to the supply, you can connect gate of the transistor to the output, or you can connect gate of the transistor to the VSS, means ground plane, right? So the gate of the transistor for a single transistor replacing the entire pull-up network can go with supply, can go with ground, or can go with the output, giving rise to many different types of. So none of this ratio logic design is widely used in any actual application. This one and this one has very limited application. So we will look into the operation of this one and this one. So first look at what is the major advantage of this design. Why people even explore that design, that possibility. So let's talk about this one. How many transistors we need? 2n, n being the input, 16 transistors. If we go by this design, number D, how many transistors we need? 8 plus 1. Because one PMOS transistor in the pull-up network replacing the entire pull-up network. So this one needs only 8 plus 1, n plus 1 I should say. So 9 transistors, right? So the advantage is I will be saving just for an 8 input NAND gate, I will be saving almost 50% of the chip resource, because most important, the most expensive chip resource is the transistors, because you need transistor to implement those functions. So it is n plus 1 as opposed to 2n. For a 10 input, I need 11 here, I need 20 here. So I'm saving almost 50% of the circuit resources. So from implementation point of view, it looks like that within the same real estate space of 2 to 3 centimeter IC chip area, if you can use less number of transistors for logic gates, then you have more free transistor available to you to add more transistor, add more apps and functions to your cell phone device, right? But still we don't do that. Because the biggest disadvantage of this is any of these options will never be able to give us a full voltage swing. That means ground to VDD. 0, binary 0 exactly at ground, binary 1 exactly at 1, that is called full swing, full strength voltage, full strength binary signal. But this one will never be able to give you full strength. It will always have an imperfect output low. Binary 0 will be always distorted above 0. It will always stay at slightly above ground. So it will be distorted and noise can, smaller amount of noise can flip it and destroy the binary value. And another bigger, and why I will explain it. Why it has a distorted low output. It will have a static power consumption. Ideally, a CMOS logic gate, the way it works, when you reach steady state 0 and steady state 1 here, transition is over. Either this one is off or this one is off. There is no direct connection from supply to ground. So at steady state, this one is not taking away any energy from the battery. Ideally, static power consumption for this circuit is 0. But this one, for half of the time, it will continuously draw. Even if you reach your desired value of 0 and 1, half of the time it will consume power, it will drain energy out of the battery. Because of the distorted input low and the way it makes transition, its voltage transfer characteristics will be highly asymmetrical. It will not be like symmetrical like the CMOS. Highly asymmetrical. Due to the reduced voltage swing, it will have lower noise margin. So this circuit will have reduced robustness against noise disturbance. So these are the very critical and negative property. So disadvantage of this type of circuit. That's why we do not use it. Now the question is, let us see why it will have a distorted. These two are dependent on these two. Why it will have a distorted logic 0, that is logic 0 will be always above ground, so it will be imperfect output low, and why it will always consume static power. We will explain it using example A and example B. This nobody uses, so we forget about it, but it is in the same explanation. So here I am showing you. So among these four, this one is used. Now if I compare this one with this one, let's say we'll ignore this. I'm just showing you for information purposes. But let us compare with this one and this one. What is the difference? This one needs a physical resistance. On the other hand, this one is a transistor based. Putting a physical resistance inside the chip layer is a very, very difficult task because resistance are bulky. It will take a huge area from your interconnect wire and it will introduce lots of additional parasitics, heat and everything. So embedding a physical resistance inside transistor network is difficult and it is not recommended because all the parasitics and area, power consumption and thermal stress it will produce. So between these two options, the transistor-based option looks better. So here, a PMOS transistor is permanently connected to ground. What does it mean? That PMOS transistor will always on. When a PMOS transistor has an input signal of ground, it is on, right? if I connect it permanently to the ground, that is VSS or ground, whatever you call it, that means this PMOS will be permanently on. That is the path between output and VDD will always on. Similarly here, it's a physical resistance, it's not a switch. Connected between supply and VDD, so it will always remain on. We can never turn it off because we are not applying any input signal to the transistor. Here, no way to apply an input signal because it's a two-terminal device. Here, that input is permanently connected to ground. So this implementation is called pseudo-NMOS implementation of the logic function, and it is known as pseudo-NMOS logic gate. So we have CMOS, and now we have pseudo-NMOS. Why it is called pseudo-NMOS? Because this circuit is implemented by NMOS network only, class 1 PMOS. So it is not purely NMOS, it is pseudo-NMOS. So now let us implement a 4-input NOR gate and 4-input NAND gate. Yes.
So if there's always a connection between VDD and the output,
Yeah.
what would be even the point of putting an input in there? And it always be sending
You
a
actually,
VDD symbol?
yeah. That's why it is called ratio design. You're saying that if that path is always on, then how do you even make a change? Because there is no input you are applying.
So whatever input you put, it's always
Yeah,
sending a point.
yeah.
So what's the point of that?
That's what actually we are going to explain right now.
Okay.
So that's why in the ratio design, because that path is always on, it is impossible to bring down the output all the way down to ground because VDD will keep injecting charge into the output continuously. Then how do we make the change? Let's explain that. So a 4-input NOR gate in pseudo-NMOS circuit style, 4 of them will appear in parallel in NMOS network because it's a NOR with 1 PMOS permanently grounded, so it is always on. In case of NAND, 4 of them will appear in series. Now the question is, how do we make sure that in any of this logic circuit, this will actually can operate as a logic circuit. So for, let's focus on this. Let's say the input signal is A1, B1, C and D equal 0. Right? For that input signal, both of them are on, both these two are off. That means for that given input signal, from the definition of a NAND gate, we know that output F should be 1. So here, output is already permanently connected to VDD. So it is by default giving you a 1, right? So for that input combination, for any other input combination except A, B, C, D 1, output should be 1. That is the definition of NAND gate, right? A NAND gate will give you a low input only when all the inputs in the series path are 1. So the only input combination, only for A equal, B equal, C equal, D equal 1, F will be 0. That is the NAND gate. Basic definition of NAND gate. All input must be 1 for the output to be 0. So now let's assume that all inputs are 1. So this is on, this is on, this is on, this is on. Now the definition of ratio logic is coming. So all 4 of them are on. Output has a connection to ground. So these 4 transistors together through this series path will try to discharge the output to make a high to low transition to produce a binary 0 here. Because for that input combination, the very basic definition of NAND is F should be 0, output should be 0. But this one is permanently on, it will keep charging output, while these four are trying to discharge it. So now we have a race condition. That permanently on PMOS will try to keep output at 1 by charging the load capacitance CL. These four series connected on transistor will try to discharge it and produce my desired logic value output 0. So it's like a water tank. One pipe is filling, the other pipe is emptying the tank. Will the water level go down or remain at higher level? How it will be decided? If the one emptying the tank, if it can discharge water at a much faster rate or much faster volume per second than the one filling it, then the water level will go down and down. If the discharging side is much wider pipe, much stronger transistor compared to the one charging, then it will quickly discharge and go close to the bottom of the tank. That is my ground. But it will never be able to completely empty it because something is always pouring in. So, but to use it as a logic circuit, here is my ideal 0 level, ground. Ideal 0 level, and above it, I know that there is a voltage called threshold voltage, right? So I have to bring down this at least here, slightly below the threshold voltage, because that's my noise margin low. This is, or actually VIH, V input, output low. So this is where valid 0. So I have to bring it down to here, below that VIL level, into the noise margin low, to consider it as valid 0. So now, one of them is charging this PMOS, the other one is discharging. Let's say this is discharge current, this is charge current. So the discharge current must be significantly greater than the charge current, so that I can bring it down to here, close to 0 but not perfectly 0, so that I can consider it as a valid 0. So, how can we make that discharge current significantly, several order larger than the charging current, so that I can bring it down close to 0 within that valid 0 range? Only way I can do that if the resistances, equivalent resistances of 4 transistors, what? They are in series, right? So here, I am talking about 4 transistors in series. Rn equivalent is 4Rn, because assume that they are all equal transistors. And then Rp equivalent is what? Rp equivalent is just 1 Rp, because there is 1 transistor. So 4Rn combinedly must be significantly less than Rp. Other than that, I cannot make sure that ID is significantly larger than IC current, charging current. Only then I can take it down. That means 4 series transistors combinedly should be significantly less than the resistance of 100. So each of these transistors must be 20 to 30 times wider individually than this transistor. And if we have to calculate for what size ratio between this PMOS and each of these NMOS I can reach here. You have to continuously keep increasing the size of each individual transistor until you can bring down the If you have like a close relative size, close to each other, probably it will stop somewhere here or here. So for this circuit to work as a 4-input NAND gate, I have to find that minimum specific size ratio. Other than that, it will be stuck in the undefined region where it is neither 1 nor 0. So this type of circuit, to be used it as a logic circuit, it needs to satisfy a minimum size ratio between the individual NMOS transistor and that PMOS transistor. Or in case of other combination, those two NMOS transistors here, in these two cases. So that means, by definition, you cannot make this circuit symmetrical. By definition, you cannot make the circuit with equal transistor. One side of the transistor must be so large that individually their resistance is, in a 4-input NAND gate, individually each one of these transistors should have less than 25% of the resistance of this one, right? Only then you can make sure that 4 of these Rn together is significantly less than this. So you have the size ratio between each individual transistor and the single transistor has to be more than 10, 20 or 30. So that's why it is called ratio design. If you cannot satisfy that ratio, size ratio between the NMOS and PMOS transistor in the circuit, or pull down and pull up transistor, then the circuit will not behave as a logic circuit. Because logic circuit, even if it is distorted 0, it has to produce a low output in this range. Right? And in case of higher size signal, it has to produce an high output signal in this range. Right here, close to VDD. This is my valid one. So that's why, because of the, and now, when you are discharging it to make a high to low transition, that path is never turned off. That is permanently connected. First, you make the circuit asymmetrical. This side is super large, 20, 30 times larger than this one. Plus, this is constantly on, and whenever this is on, you are making a high to low transition. Battery will continuously leak power to the ground because there is a direct power. This side is on, that side is always on. So it will continuously drain power and steady power consumption. Even if you reach that acceptable low level, this path must remain on to maintain that low level, and that side is always on. So battery will keep draining energy. So from energy perspective, it is very inefficient because it will continuously drain your battery. And from circuit performance point of view, one side is always distorted. So slight variation or noise injection will push it up and you lose the logic signal. And circuit, so now earlier we said that we need only n plus 1 transistor versus twice n for CMOS. But if each individual transistor has to be 20 times larger than this one, then there is no gain actually you are achieving by making them much, much larger or reducing the number of transistors. So even those reduced number of transistors will consume significantly more area than the twice the number of transistors you will be using in CMOS. So that's why ratio logic design, whether it's resistance based or zero NMOS transistor, logic circuit, we don't use it. Does it clear your confusion?
Yes.
Yeah. So now, let us look at the classification again. We will repeat this slide many, many times. So, we are still looking at combinational logic circuit. We haven't started sequential yet. We are looking at static logic circuit. We have started dynamic circuit yet. We looked at CMOS circuit. Now we just explain ratioed logic. The first one is called resistive load. Now it is clear to you. This is called resistive load, ratioed logic circuit, and then this has some name, and this is pseudo and MOS. So we explained you how pseudo and MOS works. Similarly, resistive load exactly same thing. And then differential cascade voltage logic is a special application of resistive load to basically overcome some of the limitation of the resistive load. Again, this is not very widely used, but we will look into it. And then a completely different logic circuit style is called pass transistor logic style. And a special case of pass transistor logic is transmission gate. So this circuit will introduce you all the different types of logic circuit. Yes.
So within all of the ratioed logic circuits, do they all work the same?
Exactly the way we discussed, because if you look at this version, we are using, let's compare with this one to this one. Instead of PMOS transistor, we are using an NMOS transistor. This PMOS is permanently connected to ground, so it is always on. This NMOS is permanently connected to supply, it is always on. So the analysis, what we just analyzed, will be exactly the same. Instead of an NMOS load, we are using a PMOS load. Here, but when they are permanently on, how they are behaving? They are just behaving as simple resistor. When a transistor is permanently on, between the terminals, it is representing an on resistance, right? So this one, and this one, these three are exactly same thing. We are replacing the pull-up network with a simple resistance. Here we are using a physical resistance. Here we are using a permanently on NMOS transistor as a resistance. We are taking its on resistance. Here we are using a permanently on PMOS transistor as a resistance. This one is slightly dependent. It is dependent on output. If the output is 1, it will be on. If output is 0, it will be 0. So, but same operation. So if you are asked to implement any given logic circuit given to you using pseudo NMOS or resistive load or enhancement mode, what do? You draw the NMOS network. In case of PMOS network, if it is a pseudo NMOS, you just put one PMOS transistor, ground it. In case of resistive load, you draw the pull down network, just put a resistance between output and the supply. In case of enhancement or saturation mode, you put an NMOS transistor and connect it permanently to the VDD. That's it. You have, or in case of depletion mode, connect it to the output. So all you need to know. That's why I don't know whether you asked or somebody else. Why not we always start with the PMOS pull-up network? Because pull-down network is more frequently used in many different types of logic types. So if you know how to draw or design the pull-down network, and if you need a pull-up network, it will be just complementary. Change the transistor, change the connection. So know this pull-down network. So this is a new logic style. Now we are going to see quickly this DCBSL. So one of the problems with ratio logic design is that it is not able to give us full voltage swing because it will always give us imperfect logic low. Imperfect logic low because logic low will be distorted. To overcome this limitation of ratio logic circuit, they came up with a solution if there is a situation that you have to use ratio logic. That is called DCBSL. Differential cascade voltage switch. It is used as a switch in some. So the design goal is to design a ratio logic circuit that can provide full rail-to-rail, full voltage swing, ideal ground and ideal VDD, binary 0 and binary 1. and to ensure that it doesn't have static power consumption. What we explained here, this one has a direct path from VDD to ground because both sides are on, so it will continuously consume static power. So it has two biggest disadvantages: not having full voltage swing, distorted output low, and having static power consumption continuously. To avoid these two biggest disadvantages of ratio logic, they came up with this DCBSL. It's basically a double design. So in this DCBSL design, instead of one, it will have two pull-down networks. Pull-down 1 will be complementary of pull-down 2. Whenever we say complementary, means pull-down 1 and pull-down 2, both pull-down, so both should be made of NMOS transistor. But they are complementary in connection. Pull-down 1 will be regular usual pull-down 1. Series for NAND, parallel for NOR. Pull-down 2 will be complementary. Parallel connection will become series, series connection will become parallel. By that way, and then in regular pseudo NMOS logic, PMOS transistors were grounded. Here too, we will have two load device, M1 and M2. One of them will be connected to the other output. So this circuit now will have two outputs. If you are implementing a 4-input NAND gate, your output will give that NAND, your other one will be output bar, it will give you an AND. So this circuit, another advantage is this circuit, the way it is designed, complementary in horizontal direction. If this one is on, this one will be off. If this one is on, this one will be off. And they will on and off disconnect. So if this one is off, on, it will turn off that one, so it will disconnect battery from pull down one. If this one is on, it will turn off that load transistor, so pull down 2 will be disconnected from VDD. So they will basically turn on and off alternatively, so that there is no direct connection at any point from VDD to ground to avoid the continuous static power supply. And then because of that complementary connection, they can discharge the output all the way to 0. Wherever it stops, it will take it to the next level. That's how the connections are made. So if we draw some example, it will be clear. One thing you have to remember, pull down 1 will be regular pull down. So pull down 1 and the transistor amp together, it is giving us a 1 0 NMOS transistor. And then its complementary version will be pull down 2 will be complementary, not in terms of transistor. Pull down NMOS transistor, series become parallel, parallel becomes series. To make sure that if this is on, this is off, if this is off, this is on. Right? And then they will activate the transistor this way, diagonally. Because it is connecting to the ground, I am connecting this one to this output, that one to that output. So this will give us full rail-to-rail voltages all the way to ideal 0 to ideal 1, and it will stop static power connection because vertically for each individual VDD to ground, there will be no connection when they are on and off. So it will reduce, it will avoid the static power consumption. Another advantage is, in this logic gate, both NAND and its unbound AND, NOR and OR, both will be available simultaneously. In any traditional logic implementation, if this is an 8-input NAND, right? If I want the AND of that 8, I have to put an inverter here. So here I get NAND, here I get AND. Let's say this is my signal F, this is my signal F bar. So between F and F bar, there will be always a delay of 1 inverter. But in many logic expression, you will see that the function is some y equal to AF plus BC F bar, something like that, right? It can happen, right? So both the expression needs both F and F bar together in the same function. And if this is the source of F and F bar, between them, in the traditional CMOS implementation, you cannot make this delay 0 because it's a physical inverter. So you will get F and F bar after one inverter delay. So this logic expression must include the delay of the inverter associated when you are doing the time calculation. You have to add that. But here, both of them, whenever you get F here, F bar will be automatically available here. So both signal output and its invert simultaneously available. So there is the third advantage. Disadvantage is, well, it is still ratio logic circuit. These transistors has to be significantly larger individually than the single load transistor, you have all other disadvantages, but only thing we are avoiding the static power consumption, avoiding the reduced voltage swing, and also adding an option to get signal and signal bar invert at the same time. So, but as I said, this is hardly used and the resources are double. We are not saving anything here. So what is the implementation? So for CMOS and MOS, it is n plus 1. For CMOS, it is twice n. For this one is twice n plus 2, right? Twice n plus 2. That is what we need in the CMOS and MOS. So for DCDSL, twice n plus 2. So we are actually wasting more circuit resources. And the circuit is heavily ratio designed. So that's why it is hardly used. So this is just an example of a DCBSL using a 2-input AND NAND. So this side is pull down network 1. NAND, so AB will appear in series. So in this corresponding output, I will get, this is NAND, sorry, this is NAND, this should be NAND, and this is an output bar. The bar is missing here, or it is in the slide, but somehow it is not showing up here. And pull down 2 will be parallel. This is an XOR XNOR gate implementation in DCBSL. So if I give you any random function like this example in the slide, if I ask you to do the DCBSL first serial and MOS version of this, what do? You draw this block, pull down one block. In case of resistive load, put a resistor here. In case of pseudo and MOS, put a PMOS transistor, permanently ground it. In case of DCBSL, draw pull down network 1 and then draw the pull down network 2 on the side. Series becomes parallel, parallel becomes series, right? And then 2 PMOS transistor, cross connect them. So now as you can see, these are all interdependent. If you know how to construct pull down network for any logic circuit, everything will be built onto that. Only difference is first transistor logic. So we will not start it today. So we will end here on slide 37. So a couple of you have missed quizzes with prior permission, medical leave, or out of state conference travel. So what I'm going to do is, because you guys are too busy with preparation for quiz 4 and midterm, I will arrange those makeup quiz, those who had prior permission to miss those quiz and one person who missed the bus. I will arrange those makeup quiz after the midterm. Because right now I don't want to divert the attention. So important thing is that you spend a lot of time on lecture 2 and 3. And then on lecture 4, only thing you need to know, the main thing, not only thing, the main thing you need to know, how to construct the pull-down network. Everything else you can just build on it. So, Monday, Tuesday, and also Thursday. Next week, 3 days, I will be available in my office from 1 to 2:15. So you can stop by, no prior appointment is needed for any help regarding the contents from lecture 1 to 5. Okay?
So,
See, yes.
now we have completed the 37 slides.
Yeah.
On this
So quiz 4 will be actually, there will be nothing from past on this. So just to make sure, quiz 4 is next Tuesday. So, and it will be based on lecture 4. There will be, we did not cover past on this time. So there will be no question from past on this time.